Hello, everyone, and welcome back. In the past few videos, we've been talking about Riemann integration. And in particular, we've been asking ourselves, under what conditions can we conclude that a function is Riemann integrable? That is, its Riemann integral exists. Now, what we would like to do is extend this discussion into what we were doing when we were talking about continuous functions. And you'll recall that when we talked about continuous functions, we spent a lot of time talking about sequences of functions, and in particular, convergence of these functions. In the case of Riemann integrals, we want to ask the same questions. We would like to know that if we have a sequence of Riemann integrable functions, is the limit, if this thing converges, is the limit going to be Riemann integral itself? And if I take the Riemann integral of each one of the sequential functions, does the value of that integral converge to the value of the limit? Now, you'll recall that there are two different notions of convergence when we talk about sequences of functions. We have the weaker notion of pointwise convergence, and we have the stronger notion of uniform convergence. Pointwise convergence tells you for each value in the domain, you converge to a real number. What uniform convergence tells you is that convergence happens over the entire domain all together. And we saw that this is captured by the supremum norm. And in fact, uniform convergence is so strong that we saw that when you have a sequence of continuous functions, your uniform limit is going to be continuous as well. So if you have uniform convergence, you get a uniformly continuous limit. Pointwise convergence doesn't give you this. So what we're going to investigate is the analogous scenario here for Riemann integrable functions. And as you can probably guess, pointwise convergence is not going to be strong enough in order to capture or in order to say that the limit is Riemann integrable and that you have these integrals of the sequence converging to the integral of the limit. But what we will prove today is that when you have uniform convergence, then you get convergence of these integrals as well. So what I want to do is I want to start with a couple examples that will illustrate exactly where pointwise convergence fails, and then we'll move into a main theorem that tells us that uniform convergence is what we want here. Okay, so let's start with an example. And the example that I'd like to start with uses the fact that the rational numbers are countable. So recall that Q is countable. And so the set S, which is going to be the rational numbers between 0 and 1, is also countable. Now, the reason for this is because countability tells us that we can arrange all of the elements of our sequence, or all of our elements of our set, into a sequence. So then if we just look at the elements between 0 and 1, that moves us to a subsequence. So that means that we can still enumerate the elements of S as a sequence as well. So we can say let S equal to a sequence of rational numbers. I'm going to call them Q sub n. And in this case, this is going to be all of the rational numbers between 0 and 1. So now let's define a function. Let's call it f sub n of x, which takes the value 1 if the value of x that's given is one of the first n rational numbers in this sequence that enumerates S. So it doesn't matter how you enumerate it. The fact is you can do it. And once you have that sequence solidified, then you can ask yourself, what are the first n values? If I put in an x, then I get 1 here. But otherwise, I would get 0. And this is for all x in 0, 1. Now, what I'm going to leave for you is you can check the integral of this thing, since it only has finitely many points where it's equal to 1 and it's 0 everywhere else. So we find that the Riemann integral over the domain of each one of these things is equal to 0. And Fn of x converges to what we call the indicator function of the set S, where the indicator function indicates whether or not you have put an element of S into your function. So it gives you 1 if X is in S, and it gives 0 if X is in 0, 1 minus S. So this is going to give you 1 when you put in a rational number between 0 and 1, and 0 if you put in an irrational number. And this convergence, this happens pointwise. So maybe I should just write this underneath. This is pointwise. So you can easily check this. Just pick a value of X. If it's a rational number, then after some n, it's going to be included in the sequence here. And so Fn of that rational number is going to be 1 beyond, the value of n where this thing shows up in the sequence. Otherwise, you just get a sequence of zeros. So it's fairly easy to see that we get convergence here. But we've already shown that this indicator function on the set S is not a Riemann integrable function on 0, 1. Remember, we proved this back when we first introduced Riemann integrable functions. So in the first lecture on integration. So what this shows us is that even if we have a sequence of Riemann integrable functions, we do not necessarily guarantee that the limit, the pointwise limit of this thing is going to be Riemann integrable. So this is an issue, right? Pointwise convergence is still a problem for us. Okay, so maybe you might have the following question. You might say, okay, what if I know that the limit is Riemann integrable? Then can I say that the integrals converge here? And it turns out that this is not true either. So pointwise convergence fails again for us. So let's look at another sequence of functions. I'm going to say Fn of x, this is equal to n if 0 is less than x, which is less than or equal to 1 over n. It's going to be 0 if 1 over n is less than x, which is less than or equal to 1. And it's also going to be 0 if x is equal to 0. Sorry, this should be a strict inequality here. And so what does this function look like? Well, it's just a little tiny bump between 0 and 1 over n. So all it is here is something that looks like this. And then, so we have some discontinuity here. This thing goes all the way up to 1. And down here is 1 over n. So this is Fn of x. And this is for all natural numbers n. So what we can see here is that we have pointwise convergence. So notice Fn of x converges to f of x, which is just the 0 function, pointwise. Now, how do you see that? Well, if you pick some value of x in the domain, then the Archimedean property tells you that there's a big enough n so that 1 over n is smaller than that value of x. And so you're eventually going to hit a sequence of all zeros. And so then your pointwise limit is always going to be 0 because you have, for every value in the domain, you have a sequence that is eventually just all zeros. So this is pointwise on 0, 1. Also, you can prove that Fn is Riemann integrable. This is a fairly easy thing to do. You can go ahead and try this on your own. I'm just using these as illustrations, so we're not going to go through the proof here. And its limit, the 0 function, is clearly Riemann integrable as well. But here's the kicker. Here's the problem. If I take the Riemann integral of Fn of x, well, you can easily check again, if this is just if we think of this as the area, it's this area inside of or underneath this little triangular wedge. That thing is equal to exactly 1. And so this area is equal to 1 for all n, which clearly converges to 1 as n goes to infinity. But this does not equal to 0, which is the integral of the limit here. So what this one tells you is that when you have pointwise convergence, even if your pointwise limit is going to be Riemann integrable, you still can't say that the limits are equal to each other when I take Riemann integrals. So let me put that in words. So that is, it is false in general that you can say this. If I say, what is the limit of Riemann integrals over a domain? You cannot say that this is the same as just integrating the limits or integrating the limit when you have pointwise convergence. So the question is, when is this actually true? When can I actually do this? Well, as you can probably guess, we've been playing with pointwise convergence. That's where all the problems arise. So that means that uniform convergence probably does the trick here. And that's going to be our next theorem. So let's assume, suppose we have a sequence of Riemann integrable functions. So that is, we have Fn belonging to R of AB for all n greater than or equal to 1. And suppose Fn converges to F uniformly on AB. So maybe you forgot about uniform convergence. It's been a while since we've spoken about it. You might have to go back and refresh yourself. But then, similar to what we saw with a sequence of continuous functions, our limit here is also going to be a Riemann integrable function. And we have that property that I just listed above that I said does not true in general. Well, now it is true. We can see that the sequence of the integrals is equal to the integral or converges to the integral of the limit. So that tells us uniform convergence is the convergence that we want to talk about. We already knew this, right? We talked about uniform convergence when we talked about continuous functions. We saw that was the desirable type of convergence. Pointwise is just too weak. It can't get the job done for us. So what we're going to do is we're going to use the Darboux criterion. So we will use the Darboux criterion to prove f is a Riemann integrable function on AB. So that's the first thing. We want to show that it's Riemann integrable, and then we're going to show that those limits pass inside the integrals. So, of course, if we're going to use the Riemann, or if we want to show the Darboux criterion, we need an epsilon. We're going to show the upper sum minus the lower sum is less than epsilon. So then there exists some capital N such that if we look in the sequence beyond that capital N, this implies, remember, uniform convergence is in the sup norm. So this tells us the sup norm of the difference between Fn and F. We can say that this is as small as we want it because it goes to 0. In our case, we're going to use epsilon over 3b minus a. And so we can see the length of the domain coming in there, b minus a. We see the over 3. That tells us that there's going to be a triangle inequality coming into this. And so let's keep going. Okay, also, while there exists a delta greater than 0, since these things are Riemann integrable, such that if I take the mesh less than delta, this implies that the upper sum of f sub capital N, so the first element of this sequence where the above inequality is true for the sup norm, I need to fix an actual value. Actually, let's put this on the next line so it fits. Fn of p minus the lower sum of Fn of p is less than epsilon over 3. So that's just Darboux's criterion for the integrable function f sub capital N. Remember, our assumption is that we have a sequence of integrable functions. So fixing an index value at capital N, that thing is integrable. Okay, so let's let P be a partition. So this gives us our partition of the domain. Actually, let's use M here so that things don't get confusing, because we're using little n as the sequence. Be such that we have this thing less than delta, so the above inequality holds. And let's observe. So observe that on each subinterval, our xi minus 1 to xi, we have, all right. So what we're going to do is we're going to unpack this inequality right here. We know that that tells us, maybe if I just put in blue, actually, let's put it in green so it pops a little bit. This thing is Fn of x minus f of x. And this happens for all x in the domain, of course, because this is the maximal difference, the supremum, or in the sup norm. So I'm just going to unpack that so you can see where this is coming from. Well, then the infimum value of f sub capital N, which I'm going to call m sub, pardon me, sub I of capital N, minus epsilon over 3b minus a, since I'm going to unpack that starred inequality above, that is less than or equal to Fn of x minus epsilon over 3 times b minus a. And that is just using the fact that I've got the infimum of my function f sub n of x. So I've just subtracted the epsilon over 3b minus a from both sides. Then from my red starred inequality up there, this tells me this is smaller than f of x, which again from the starred inequality tells me this is smaller than Fn of x plus epsilon over 3 times b minus a. So essentially the value of f of x is bounded between Fn of x minus epsilon over 3 times b minus a and Fn of x plus 3 times b minus a. That's what the starred inequality tells us if we unpack it a little bit. And of course, I'm going to make this smaller than the maximum value of Fn of x. Remember, these things are Riemann integrable. They're bounded, so these things always exist, these max and min values. And so here we have it. And let's just put this on another page just so we know where am I. This is the sup of Fn on each subinterval. And m sub I capital N is the inf of Fn on each subinterval. Just so you know, just so you have it for your notes. Okay, so thus, this tells us that m sub I sub to the capital N minus epsilon over 3 times b minus a. Now, this is, let me take a look at this. Since this inequality holds for all x in the domain, so this is, for all x in AB, well, we can replace, let's put a little star beside it so you know what I'm looking at. This piece right here, this can happen for the infimum of f of x or for the supremum of f of x. So that tells us that this is less than or equal to m sub I. Now I don't have a capital N subscript because this is equal to, so this, let's just write it, inf f on xi minus 1 xi. And then this is, of course, less than or equal to the sup just by definition. So maybe just writing that in again, this is sup f on xi minus 1 xi. So these are just the infant sups of the limiting function f. And of course, by the same argument that I just made with the infimum, this is less than or equal to this. Okay. So this gives me everything I need because of that inequality at the top, that string of inequalities gives me the following. Hence, if I look at the upper sum of f with respect to this mesh and the lower sum with respect to this mesh, well, by definition, so just by definition here, we've got I equal 1 to m, remember? Capital M sub I minus little m sub I delta xi. This is just the definition of the upper sum minus the lower sum for the limiting function. But we can use that string of inequalities above, and this gives me that I is equal to 1 to m, and then I get mi to the n minus mi to the n plus 2 epsilon over 3 times b minus a. So that comes from, if I just underline it, one of them comes from right there, the other one comes from right there. So they're both coming into that. I have 2 of them. I've got delta xi here. But the capital Mi to the n minus little mi to the n, that is just the upper sum of f sub n with respect to the mesh minus the lower sum of f sub n with respect to the mesh. And the last piece of this, I've got 2 epsilon over 3 divided by b minus a, and then a sum of delta xi's. We've seen the sum of delta xi's is equal to the length of the interval b minus a. So that leaves me with 2 epsilon over 3, since the b minus a in the denominator is canceled. And we've already seen that when we have that mesh, we can make that upper sum minus the lower sum for the function f less than epsilon over 3. And here we go. We have that this is less than epsilon. So thus, our limiting element is Riemann integrable by Darboux's criterion. Okay, so now we need to show that if we go back to the statement, we now need to show that our integrals converge to each other. So here's what we'll do. So now, if we take our absolute value of the difference between these integrals minus the integral from a to b of f of x dx, well, the first thing we can do is we can combine these integrals from the linearity property of my integrals. So I get fn of x minus f of x dx. Then what I can do, since the inside of this thing can be positive or negative, this is less than or equal to putting the absolute value inside of the integral, because when I do this, I make the integrand entirely positive. That means there's no negative area coming in. I took all the negative area, made it positive as well. So that's where the inequality here comes from. And then I've also got the integral from a to b. Well, the maximal difference between fn of x and f of x over the entire domain is bounded by the sup norm between fn and f, which is equal to the sup norm between f and f times the length of the domain, because now we're integrating a constant function. And this thing goes to 0 as n goes to infinity, which shows us that these integrals converge to each other. So that gives us the completion of the proof. So once we know it's Riemann integrable, that means that this piece right here actually exists, and therefore I can just do this really, really quick chain of equalities here, or inequalities, to show convergence. Okay, so what does this tell us? It tells us uniform convergence is again what we care about, right? It is the property of function convergence that means a lot to us. Now, what I want to do is I want to pull this up and make things abstract again. I want to go back to general vector spaces and show you sort of how this fits into a larger mosaic of mathematics. So bear with me, I've got a little definition for you. So let's say if V is a vector space, we've already learned about vector spaces. And it also has a norm. We've learned about norms. So we're going to make things abstract again. We're going to just call that norm the double lines. So we call a function t that goes from the vector space into R a linear functional. Remember, we saw this already. I'm putting a proper definition on it now, but we've seen this in the context of integrals already. Well, this is a linear functional provided t of alpha x plus y is equal to alpha t of x plus t of y. So you have this distributive property for all x and y in your vector space and real numbers alpha. Then we say that a sequence xn converges to x in V if and only if the norm of the difference between those things goes to 0 as n goes to infinity. So this is an abstract notion of convergence in a general vector space equipped with a norm. But if you want to keep it tangible, just replace the vector space with the space of continuous functions, and the norm becomes the sup norm. This is just uniform convergence, right? Okay, then let's keep going. A linear functional. So a linear functional t is called continuous it's called continuous if and only, or continuous at a value x in V, if and only if for all sequences xn converging to x, we have t of xn is converging to t of x. Now, this is basically the sequential criterion or the sequential definition of continuity for continuous functions, right? So we don't have the epsilon delta definition here. Now we're using the sequential definition for continuity, this time on an abstract function. We're doing it on linear functionals now instead of continuous functions. And then finally, t is called just continuous. So just continuous if and only if t is continuous at all x in V. Okay, so that's a lot to digest, but we've kind of already seen this before. So let me put this into context. Let me give you a remark on how this fits together with our spaces of functions we've been talking about. So example, recall C of AB, so the continuous functions on a closed interval is a complete norm vector space. So it's a Banach space. Space with respect to the sup norm. Okay, then if we define a linear functional from the continuous functions into the real numbers by, well, if I give it a function, it's going to return to me the value of its Riemann integral. Then we've already seen that t is linear. And that comes from the fact that you can distribute the integral over sums and you can pull constants out of it. We proved this a few lectures ago. And the previous theorem shows T is continuous, right? Because we have convergence with respect to the sup norm. Well, then that theorem that we just proved says that when you have convergence with respect to the sup norm, then your linear functional T of Fn, which is the left piece of this limit here, converges to your linear functional at F, that's T of F, right? So I'm just sort of lifting all of this into the abstract, but we're still sort of saying the exact same thing. Now, what I'd like to do for the remainder of the lecture is talk a little bit about general continuous linear functionals. So we'll come back to them as we sort of move through this class. But I want to show you a really, really interesting property of these things and I want to do it in complete generality. So if you think about what we just did with the integral, we had to do a lot of work to show that it's continuous at any value, because we had to show that if there's a sequence converging to any continuous function, then you have to do all of this work. But let me show you this really, really great result that has to do with linear functionals that tells us that if you want to prove a linear functional is continuous, you just have to do it at one single point, and that single point is 0. So let's say let V be any vector space over the real numbers. Remember, we have that field notation. In this case, we're always going to take the field to be the rational numbers, equipped with a norm, which we'll just call in general here, just the 2 lines. Then we say a linear functional T from V into R is continuous. So that means it's continuous at every single every single X in V, if and only if T is continuous at 0. So if it's continuous at the 0 vector, remember the 0 vector in the space of continuous functions is just the 0 functions. We have to remember this is abstract, but nonetheless, this is an awesome result. This tells you that if you want to check continuity of a linear functional, you just have to do it at 0. So let's look at the proof here. It's actually quite elegant. It's quite simple. It's really, really nice. So the first direction, if T is continuous, then by definition, it is continuous at 0, right? So the one implication is immediately trivial, because being continuous means you're continuous at every point, and one of those points is 0. So we only need to prove the other direction. If you're continuous at 0, then we're going to show you continuous everywhere. So assume T is continuous at 0. Okay, so let's note the following. We're going to put a note in here. T of 0 is equal to, well, okay, I'm going to do something that looks really, really silly, but 0 plus 0 is always equal to 0. But from the linearity property, this tells me that I get T of 0 plus T of 0, because the functional has to distribute over sums, which is, of course, equal to just 2T of 0. So this tells me that a real number, is equal to 2 times itself. Well, of course, then T of 0 has to be equal to 0. That's the only way that this is going to work. Okay, so now, since T is continuous at 0, we're going to use the definition of this at 0. Then if I've got a sequence converging to 0 in this norm, if this is going to 0, this implies that T of xn is converging to T of 0, which is itself equal to 0, right? So I'm just writing down what the definition of this says because this is a little more abstract than we might be used to. So you have to make sure you can really follow along with all the definitions here. Okay, let X and V be arbitrary. We're going to show that we are continuous here now. Suppose Xn is converging to X, which is the same as saying, remember the notion of convergence in a vector space means you converge in the norm. And so this tells us that, so then, well, this gives that T of Xn minus T of X. If I look at this in absolute value, this is equal to, from the linearity property, Xn minus X inside of my function T, because T is a linear operator or linear functional. But then this thing right here, Xn minus X, is converging to 0. It's a sequence that goes to 0 now. So it's, remember, we talked about this really early on with null sequences. Same idea. But clearly, this thing converges to T of 0, which is equal to 0. But look what this says. So T of Xn converges to T of X. And that gives us our proof, right? So everything really just comes from the linearity property. That's what does all the work here, because that allows us to absorb these sequences all into the functional T altogether and just look at null sequences instead of sequences converging to a general value. Okay, I want to show you one more property of linear functionals before we finish. And this is going to require one more definition. So let's say a linear functional, T on a normed vector space V is called, now we call this thing bounded. It's called bounded if and only if there exists some number, we'll call it K, such that T of X is less than or equal to K times the norm of X for all X in V. So what this says is that the value of your linear functional in absolute value, evaluated at any X, it can only be so large. And its largeness is relative to how large the value of X that you actually put in there is. Again, if you want this to make a little more sense, use the sup norm, right? The sup norm tells you the sort of maximal variation of a function from the x-axis. What this is telling you is if you have a linear functional and it's bounded, it says that its value inside that linear functional is no more than a constant multiple of how far that function varies from the x-axis. Now, let me show you a really, really nice theorem that tells us that continuity and boundedness are actually the same thing. So if T is a linear functional, on a normed vector space V, then T is continuous if and only if T is bounded. Again, this is really, really nice because this tells us that that continuity and boundedness are the same thing, right? So we've already sort of reduced continuity to showing that you're continuous at 0. So now we can show that it's the same as just having continuity, or it's just showing boundedness. Okay, so to proceed with the proof, let's start with the case when T is bounded. So this is going to go from right to left. So assume T is bounded. Okay, then to show t is continuous, we show it is continuous at 0, right? Because our previous lemma tells us all you need to do is check that it's continuous at 0. So let's assume that we have a sequence converging to 0. That's what this means. Well, then this is quite easy because boundedness tells us that t at xn, this is less than or equal to k times the norm of xn. K is fixed, it doesn't change with n. So this becomes a sequence that converges to 0, which tells us t of xn converges to 0 as well, which implies t is continuous at 0. So that was easy, right? That implication was very, very easy. Boundedness implies continuity, done. And it's mostly made easy by that previous lemma that we just proved. Okay, let's look at another example, or let's look at the other implication from left to right. Let's suppose t is continuous. And this is continuous at every value of x, right? So assume t is not bounded. So we're going to argue for a contradiction here. We're going to assume that we're not bounded, and we're going to show this is impossible. So then this tells us that for all natural numbers, there exists an xn in V such that, well, t of xn can be made very large relative to the size of xn. And now what we can do is we can say, let the sequence of real numbers Cn be the square root of n multiplied by the norm of xn. And we're going to make that 1 over this. And this is going to be, since we're assuming, so since xn does not equal to 0. Of course, this has to be the case. Otherwise, this implication of not being bounded would just be useless, right? Because this is just saying t of xn is bigger than 0. So of course, we want to be able to choose a sequence of non-zero xn's. And then what we can do, since they're non-zero, by the definition of a norm, their norm is non-zero. Then this tells us that t of Cn xn, so if I stretch or compress those vectors by the factor Cn, well, by definition, this thing is, or by assumption, sorry, this is bigger than this, Cn, and then xn. So that's just using linearity, pulling out the Cn, and then using the fact that you're not bounded. And this is equal to the square root of n, because Cn is canceling off that norm of xn, and it's taking off a square root from the n. And this happens for all n in the natural numbers. So then if we denote yn equal to Cn xn, we have, well, the norm of yn, this is just equal to 1 over the square root of n. That's because the norm of xn is being canceled by the Cn term. So now what we've got is a sequence of yn's going to 0, but t of yn does not converge to 0, since t of yn, we just showed above, is bigger than the square root of n for all n greater than or equal to 1. But this contradicts the fact that t is continuous. So this contradicts that t is continuous, showing that t must be bounded, right? Because in this case, we assumed it was not bounded. And then what we were able to show is that there's a sequence converging to 0 that t of this sequence is not converging to 0. And that's a contradiction, right? Because that's continuity tells us that limits pass through these linear functionals. Okay, so this has been a relatively long lecture. So let me finish up with just one last piece of this. Let's go back. So go back to t of f is equal to the Riemann integral of f of x dx, right? So we've been doing things very, very abstractly so far, but let's bring it all back home. Now, we know, we've already shown with our theorem today that this thing is continuous, but the previous theorem just told us that continuous is the same as being bounded. So how can we show that this is bounded? We know it's bounded. We just want to know, or we want to be able to show it. Well, notice that if I take the absolute value of t of f, this is from my arguments that I made before. This is an absolute value of the integral. This is less than or equal to the integral of the absolute value, which that absolute value of the function is less than or equal to the sup norm of the function. That comes from the fact that you belong to the continuous functions. We know that this thing is bounded because you're on a closed interval. That's what the extreme value theorem tells us. And this is equal to b minus a times f in the sup norm. So very similar to what we did with the theorem at the beginning of the lecture today. But then that tells you that this thing right here is equal to k, which tells you that t of f is less than or equal to k times f in the sup norm, which implies t is bounded. Okay, so what we did today is we talked about sequences of functions, and we asked ourselves when a sequence of Riemann integrable functions converges to another Riemann integrable function, and when the values of their integrals converge to the value of the integral of the limit. Then what we did is we sort of lifted ourselves back out into the abstract realm. We talked about linear functionals, so something we've briefly seen before, but now we have a precise definition of it. And in particular, we started talking a little bit about abstract vector spaces. So we can say a lot more about linear functionals beyond just the space of Riemann integrable functions or the space of continuous functions, but for any vector space, and beyond just taking the integral of a function. There are many, many, many more linear functionals associated to these vector spaces. And now we have general results that apply to all of them.